Hello everyone, I am Premlata. I am working as an assistant professor in Guru Nanak Institute of Technology in EC department. I have completed my M.Tech from JNTU Hyderabad in VLSI and I am pursuing my PhD in I B.Tech from Anurag University. And today I would like to introduce you the field effect transistors. FET stands for field effect transistors. So field effect transistor means whenever the applied potential between the terminals, if they are controlling the flow of charge carriers across the device, it is called field effect transistor, which means that whenever the applied potential is controlling the output current, it is called field effect transistor. Likewise, here for example, if I take the example of let me take the example of water tap. So the pressure we can control here. Whenever we control this pressure, the flow of water, the pressure of the water will be controlled. So if I am taking, as we know that field effect transistors are having three terminals, one is gate, other one is source and the third terminal is drain. The pressure, whatever the knob we are controlling here, it is controlling the water flow pressure at the output. Similarly, the voltage, whatever the voltage we are applying at the gate terminal, it is going to control the current, output current, which is called drain current. So here the charge field effect transistors are of two types: junction field effect transistors and metal oxide semiconductor field effect transistors. Junction field effect transistor and metal oxide semiconductor field effect transistor. So the junction field effect transistors are also two types. They are N channel JFET and P channel JFET. Here MOSFETs are also two types: depletion type MOSFETs and enhancement MOSFETs. And depletion MOSFETs are again two types: N channel and P channel, and enhancement MOSFETs are also of two types: N channel and P channel. The type of the transistor will be decided by selecting or by choosing of substrate material. So here I would like to focus on junction field effect transistor and which is of P channel. We will discuss JFET of P type or P channel JFET we will discuss. So here I would like to give the construction and working principle, how it is going to be operated. So first let me give construction. JFET P channel construction. So to get this P channel, I have to take the substrate of, this is the substrate, this bar is P type substrate, this bar is P type substrate. That means whatever the channel is formed in this, that is of P type. P type in the sense, as all of us know that charge carriers are, majority charge carriers are positively charged. So we will be having positive charge as the majority charge. Then we will be taking the N type substrate materials. We will be doping the two terminals with heavily doped N type material. So which forms here ordinary PN junction and here also it is going to form ordinary PN junction. So there will be a depletion region and they are in the form of wedge in nature. Then let me take the three terminals. One is gate terminal, the other terminal is source and drain. There will be fourth terminal also called substrate terminal, which is in short which can be used for the future purpose. Then I am applying the potential between gate and source as VGS. The potential across gate and source terminal is VGS. Then we are also applying the potential between drain and source. It is represented with VDD. If you observe here, the substrate is of P type and material is, the gate terminal is of N type. So here there will be a ordinary PN junction construction here, and here also there will be a ordinary PN junction construction at the substrate side. So if I apply VGS, like this is N type in the sense negatively charged terminal, and here I am applying positive terminal of the external voltage. So this bias will be reverse bias, opposite charges. So we will be having reverse bias at this gate terminal, which means that in ordinary PN junction diode, if I am applying reverse bias, what happens? This is ordinary PN junction diode in which this is depletion region. Originally it is formed by combining or by concatenating the P region and N region. Here I am applying opposite terminal, negative terminal is connected to P side and positive terminal is connected to N side, which is reverse bias. Under reverse bias, what happens? The charge carriers, whatever the charge carriers are here, there are majority carriers as holes, here electrons are majority carriers. These holes will be attracted towards this negative terminal because oppositely charged carriers will be attracted. There will be attractive force between the opposite charges and there will be repulsive force between the likely charges. Then here electrons will be attracted towards the positive terminal. So that means there will be increasing in the depletion region. If you further increases this depletion width is going to be decreased, and the movement of the charge carriers which are crossed, they will be considered as the current. So as this region is more, as you are increasing the reverse bias, we will be getting lesser current, reverse current will be less. The same operation will be done at this gate terminal. So as I am applying negative potential here, this depletion width, this is the depletion region. So this depletion region will be increasing. So we will be discussing the working operation in three conditions. One is case 1, when VGS is equal to 0 and VDD also 0. That means we are not applying any potential between the VGS and VDD. So what happens when we are not having any external potential? Whatever the charge carriers are there, they will be just moving constantly. There is a constant width thickness. That means number of charge carriers which are moving from source to drain will be same. There will not be any change in the output current. So this is called uniform thickness. Uniform thickness or uniform current will be obtained at the output terminal. Coming to the second case, whenever I am increasing the VGS potential from 0 to some positive voltages. Let me apply 1 volt, plus 1 volt. So when I am applying plus 1 volt, what happens? This is negatively charged terminal and I am applying positive potential here, and I have increased the reverse voltage. So whenever I am increasing the reverse voltage, this effective width of this terminal is going to be increased. At the same time, here also it is going to be increased. So if you observe, this is the effective channel width. This is effective channel width. So previously it was up to this point, but now as if we are increasing the 1 volt, this effective width is getting decreased. So whenever charge carriers are moving across the channel from source to drain, that will be considered as the drain current, and as this effective width is reduced, the number of charge carriers reaching this drain terminal is going to be somewhat lesser than the previous case where we are having 0 voltage. So the charge carriers, as width is increased, the number of charge carriers passing along this bar, this is called effective channel, will be reduced. So further if you increase to 2 volts, what happens? Again further it is going to be reduced. Depletion width is going to be increased, but the effective channel width is going to be reduced. So that means again there will be reduction in the output current. So further if you continue this process, it reaches a particular voltage at which channel is completely blocked. Channel is completely blocked, at which there is no movement of there is no charge carriers moving from source to the drain. The voltage at which the channel is completely blocked or pinched off is called pinch off voltage. Pinch off voltage. So that means before this pinch off voltage there will be current. After reaching this pinch off voltage, there is no movement of the charge carriers. Again, if you further increase the voltage after pinch off voltage, as you all know, there will be a mechanism called breakdown voltage. So breakdown occurs. Breakdown can be done in any way. We have two methods, but any breakdown occurs here which causes the charge carriers or the current. There will be sudden increase in the current. So if you plot all these concepts in a graphical manner, it is called drain characteristics. Now let us proceed with the characteristics, how we can plot this relation or how we can relate this voltage and current. If I am taking VDS versus ID, VDS versus ID. So this VDD is also called as VDS. So if you go on increasing, initially there is 0 voltage, and if you further increases the voltage applied between the drain and source terminal, you will be having linearly varying current with respect to the voltage. So after reaching a particular voltage, it is called cutting voltage gamma, at which current reaches maximum current or maximum value, and after this we will be having fixed voltage or fixed charge carriers between the channel. So we will be getting the constant current, and after that, after further if you increase the voltage, then you will be getting the breakdown. This is for first case when you are having VGS is equal to 0, and if you increase this VGS is equal to +1, what happens? As we are having or we are increasing the reverse voltage, effective width of the channel will be reduced. So the charge magnitude of the current from the previous case at which we are applying the 0 voltage, it will be reduced. So this much of magnitude will be reduced for this case. Then further if you increase the reverse voltage, gradually the charge carriers, if you observe the curves, family of curves, they are getting down. That means the effective magnitudes are getting decreased. So this region at which we are having linear relationship, it is called ohmic region, and this is called non-ohmic region, and this breakdown at which we are getting this voltage is called breakdown voltage. After this breakdown voltage, we will be getting the sudden rise in the current, drain current. These are called drain characteristics. Similarly, we will be having transfer characteristics also. So I will be trying to show the same transfer characteristics in the left side. Transfer characteristics. In this transfer characteristics, the maximum current is called IDSS, and we will be taking for VGS. So initially when VGS is 0, we will be having maximum channel width, so we will be getting maximum current here, maximum current, and gradually if you are decreasing or if you are applying negative voltages, the magnitude, as how we have discussed, the magnitude is going to be reduced, and it reaches a particular voltage. At particular voltage, the complete current is going to be reduced. This relation is given by Shockley, and that Shockley equation is written like this: drain current ID is equal to IDSS into 1 minus VGS by VP whole square. Okay, this is called pinch off. So this relation is called Shockley equation. This is the introduction to the junction field effective transistor and the construction, operation and the characteristics. So using this junction field effective transistor, we can get the maximum amount of drain current. This is the IDSS is saturation current and ID is the current after applying the potentials across the terminals. So the symbol for this junction field effective transistors are like this. For N channel, we have 3 terminals. Arrow indicates the direction of the drain current. This is gate terminal, this is drain and this is source. This is N channel, JFET, and we have P channel, JFET. Symbol is excuse me. This is symbol for P channel. Circuit symbols. These are called circuit symbols. Okay, I hope you all understand the operation and characteristics and different symbols for the junction field effective transistor. Thank you all.